So let's start the second part. So in the morning, you saw some basic introduction to causality research, and I gave a lot of examples. This part is kind of very simple because all of us learned about statistics and graphical models, but still I would like to review several kind of essential concepts. They are really used, they are very useful and even critical in causal discovery. So we pay attention to independence, conditional independence, Gaussian distribution, and so on. So for instance, you see Gaussian distribution is so widely used, but so weird. You see why it's weird and why we can really assume that the data are non-Gaussian. And then I'll talk about the graphical models. And you can see how we can really make sure a graphical representation is causal. Okay. Again, if you have any questions, please just raise your hand. So probability theory and statistics are kind of complementary to each other, right? So probability theory is another in another world. We cannot touch anything in that world. It models the randomness in the process and try to predict something, right? But in reality, we can only do statistics. So we look at different things, we analyze the data, and then we try to derive some information, and then we can use the probability theory to do some operation in that world, and then we can make prediction back into this world, right? So this is the relationship between probability theory and statistics. By the way, some of you can read Chinese characters, right? You know, statistics. What's the Chinese characters? Let me write down. It's a bit unfair. In traditional, right? I read this because this is shared across China, Japan, Taiwan, and so on. So first one means collection, right? The second one means calculation. So basically in statistics, you just collect data and calculate something from data, and then you can say something. It's very good translation. Okay, so first of all, we have random variables. Here we are not really talking about the statistics, so let's just start with random variables. We have discrete random variables and continuous random variables. For discrete variables, we can just write down distribution table, or we can just specify the distribution, right, with the probability mass function. And for continuous variables, we can use this kind of quantity to characterize the distribution, right? This probability for the variable to be between A and B. That's nice. Later, you can see this is not so convenient. So we are going to use two things to describe probabilities. The first one is the cumulative distribution function. It's nothing but the probability for x to be smaller than or equal to some x, some value x, right here. And no matter variable is discrete or continuous, you can always use a cumulative distribution function. And if the function is differentiable, then we have the derivative right here is the probability density function for continuous variables, as you can see from here. So this is the probability density function. Of course, probability density function can be very high, right? The value can be very high as long as the integral is 1. Okay. PDF right here. And here you can see the shapes of different distributions with the same kind of center or mean and the same standard deviation right here. Gaussian distribution, you can see Gaussian Laplace distribution, uniform distribution. And right here, you can see how the samples, RID samples drawn from different distribution look right here. Okay. So, and similarly, we have a joint probability distribution, marginal ones, and joint CDF and marginal CDF, and so on. Right? It's straightforward. You just incorporate more variables, and if you consider them together, it's a joint one. If you consider a subset of variables and ignore the rest, then it's a marginal one. And we also have the definition of conditional distribution. This is definition. Remember, probability theory is nothing but a study of the consequences of some definitions and axioms underlying probabilities. So here, for discrete variables, this is the definition of the conditional probability. And this for continuous variables is similar, right? Although they should be understood in different ways. So this is conditional probability distribution. Okay, now comes a question. Suppose you have 5 coins, which are not necessarily fair. And suppose this world can be kind of mysterious. but there could be arbitrary relations. How many parameters do you need to represent the joint probability distribution of the outcomes of the five coins? How many parameters do you need? How many? 5? Do you agree? This world is kind of mysterious. Remember, we can even do prediction from, so there could be arbitrary connections.
It's on assumption.
Yeah, so basically you assume that the outcomes are not related, right? So yes, if that's the case, then 5, but without that, how many? Right, 31, 2 to the 5 minus 1. Okay, good, because in total there are 2 to the 5 number of possibilities, right? The total sum is 1, so the number for the parameter will be 2 to the 5 minus 1. Wonderful. You explicitly, you automatically use the independence assumption, right? And we can use assumption. And now you can see we can reduce the number of parameters from 31 to 5. It's a great deal. Why? Because independence allows us to do divide and conquer. Conditional independence can allow us to do the same thing. And process independence can also inspire something very similar. You see some examples. Okay, so this is independence right here. The definition basically for independence, the conditional CDF or conditional PDF would be the same as marginal. It just means that further knowing that Y will not give you any further information about X, then they are independent. So it's a very intuitive way to see irrelevance. If they are independent, there are no way for one of them to have any information about the other, further information about the other. Okay. So then if you have more than 2 variables, you can have 2 ways to define independence. You can have pairwise independence, where each pair of the variables is independent, right? Or you can have joint or mutual independence. So essentially the joint measure is the product of the separate marginal measures, as you can see from here, right? Are they equivalent? Do you think pairwise independence is equivalent to mutual independence? No. Oh, feedback. First of all, if they are mutually independent, right, then you can clearly marginalize out other variables. Then you have mutual pairwise independence, right? So I can always throw away other variables by doing integration, and then I can see pairwise independence, right? So clearly mutual independence implies pairwise independence. Is that right? Because it's just a marginalization. You throw away variables, then you have the measure, probably measure of 2 variables, right? It's pairwise independence. Good. So if variables are pairwise independent, are they mutually independent? So this is the other one. No, right? As you can see from this example. Why did I give this example? Because later I will talk about the faithfulness. This is a typical example for the faithfulness assumption in causal discovery to fail. Here we have 3 binary variables, A, B, C, and suppose A and B are independent. A and B are independent, and they are assumed to be fair. And now C is actually determined by A and B. Suppose C is 0, 1, right? Binary. If A is different from B. If A is the same as B. Right? So all variables are binary. A and B are independent. C is produced this way. Clearly, the 3 variables are not mutually independent. Is that right? Because clearly, conditional distribution of A given C, given A and B, will be different from the margin of C. Because if I know AB, I know C. This one is either 1 or 0. This one is 0.5, right? For each possible value of C. Okay, so they are not mutually independent. Do you think they are pairwise independent? Yeah, in this case, you can verify that. You can see AC are independent and BC are also independent. So you can construct such examples. they are not so intuitive because usually when we say independence, yeah, they are equivalent, right? But you can construct a lot of examples in which pairwise independence, in which variables are pairwise independent but not mutually independent, and this is a violation of faithfulness. I will explain why later. So for now, keep this example in mind. And this is known as a three-coin problem. And this example is clear, right? Now we see dependence in the world. We see dependence between, say, variables x and y. Why are they dependent? We are trying to find a way so that we can go beyond the observed data, right? We know they are dependent. Why are they dependent? Can you explain why? We are talking about Reichenbacher's common cause principle. Actually, we are trying to go beyond that. We can make the picture complete. In Reichenbacher's common cause principle, he considered two scenarios. In fact, there are three scenarios. So can you give some explanations? Why are x and y dependent in terms of causal influences? Yeah, okay, cool. So they are dependent. In the first case, they have a causal influence in between, right? A causes B or B causes A. Good. Anything else? Yeah, common cause. Generally speaking, right? Those things can generate dependence between X and A and B. Anything else? Direct causal relationship between them, common cause. Anything else? Remember, I gave an example on selection bias, right? In that world, if you consider only college students, you can see gender and IQ are dependent, right? Some time ago. So that's the A, B, even if they are independent, if you have selection, then they are dependent. And actually, if you just live in the world where you only have the selected samples, then they are always dependent. This is the case kind of in, say, to explain, this is one way to explain why a lot of genes are dependent. It's not necessary for them to really have causal relations. They have to be coupled in particular ways so that we can survive, right? So if you just analyze our genes, you can see dependence because of selection. So only when they satisfy a particular pattern so that S is 1, for instance, can the data points or subjects survive. That's why in the observed data, we always have a dependence. So there are only three ways to explain why variables are dependent. Okay, causal relationship in between, common cause, existing of common cause, or selection process. Good. Selection is actually very, very popular because we are living in just one particular world, right? Okay. Now let's look at another example. Here, we have a lot of variables, and we know that, again, suppose we are dealing with coins that are not necessarily fair. Now we know the process. The first outcome can affect the second one, and so on. And then in this case, we have n coins. How many parameters do we need? N? It's close, right? Yeah, if they are independent, we know it's n. N minus 1 is even, you mean with this kind of, you can even make it simpler compared to the independence case. Clearly, this is more complex than the independence case. Remember, if all of them are independent, then we need 5. If you have 5, if n is 5, right? So now the world is more complex, but it's not really kind of completely messy because each variable right here only depends on the previous one. So how many parameters do we need to model the joint probability distribution of the x variables? Sorry?
2 times n minus 1.
Yeah, 2 times n minus 1. Can you explain why?
First variable is one parameter.
1, right?
And for each subsequent variable depends on the parent.
Wonderful, right? And then if you try to model the conditional distribution of x2 given x1, it's basically giving each value of x1 is just nothing but a regular probability distribution, right? You have one parameter because x2 has 2 possibilities, right? But x1 also has 2 possibilities. That's why it's 2. You have you need 2 parameters to model conditional distribution of xn given xn minus 1. So in total is 2 times n minus 1. It's more complex. It's still linear, right? Compared to the completely massive world, you can still benefit from in this kind of relationship. What relationship? It just means that when you try to model x3, you can safely ignore x1, right? This is nothing but the conditional independence. So basically, it says the distribution of xy given z is the product of the 2 separate conditional distributions, or equivalent, we can say x given y, z together is the same as x given y, x given z. So that means when I try to say something about x, as long as I condition on z already, I can just ignore y. Meaning that given z, y does not contain any information about x. Right? That's conditional independence. It's also very intuitive. Okay. This is the conditional independence. And right here, you can see some properties of independent conditional independence. Sorry about that. So first of all, clearly it's symmetric. And second of all, you can go from this kind of complex independence relationship to simple ones with decomposition. And here with weak unit, you can go from independent to conditional independence, as you can see from here. And this is the contraction. You can go from simple independent relationship and conditional independent relationship to more complex independent relationships. And they can be easily proved. For instance, for this one, you can go from this independence to this independence, right? You just do marginalization. You throw away one variable, then you have independence between x and a. If you know the independence between x and ab together, and so on. And similarly, if you put them together, this one and this one and this one together, you have the independent. You can go from complex independent relations to conditional independent relations. Okay, so they are quite intuitive. Here you can see a recap. Recap on covariance and correlation. So covariance is nothing but the expected product of the variables after you center them, right? So it's just expectation of product. We said variable are uncorrelated if the correlation is 0, and we have normalized version of covariance, which is the correlation. So essentially, you just use the standard deviation to normalize them. Okay. Okay. If 2 variables or multiple variables are independent, are they uncorrelated? Yeah, how you can easily show that, right? Because if the joint probability distribution can be written as the product of separate ones, and they can see expectation of the product would be the product of expectation, separate expectations, right? So you can go from independent to uncorrelatedness very easily. How about the reverse direction? If variables are uncorrelated, are they independent? Sorry? Yeah, good. So very often times, right, we know that, yes, in one case it's true. Generally speaking, in other cases, that's not true. In a Gaussian case, if variables are uncorrelated, then they are independent. So this normal distribution is so simple, it's so smooth that we just need 2 parameters to characterize the distribution, right? One is the center or mean, the other is the standard deviation or variance. So we have so few parameters just because the distribution is so structured, right? So weird. Okay, so the Gaussian distribution, and right here you can see the multivariate Gaussian distribution. And we just said, if the distribution is Gaussian, then independence is equivalent to 0 correlation, right? So here we assume that the variables follow joint Gaussian distribution. Okay, now comes the next question. If 2 variables are Gaussian, each of them is Gaussian, do you think they are jointly Gaussian? Can you give an example? you can construct a lot of examples, right? So for instance, suppose X is standard normal. X is standard normal. I don't know why it's so noisy. So suppose X is a standard normal. Then there are so many ways to construct another normal variable. Say Y equals X or minus X randomly, right? With random sign. Then do you think X, Y are jointly normal? Clearly, Y will also be normal, right? Because the X distribution is symmetric. Now you just have just randomly flip the value, right? So do you think X, Y will be jointly normal? The scatter plot will be something like this. Right? All data points will be on the two lines. Clearly, it's not normal distribution, right? So, and in this case, you can see that although the correlation is 0, they are not correlated. Clearly, they are not independent. They are significantly dependent. If I know the value of X, I know there are only 2 possible values for Y, right? So now you can see, yes, if variables follow joint Gaussian distribution or multivariate normal distribution, then independence is equivalent to 0 correlation. Otherwise, that may not be the case. And you can easily construct a lot of examples in which variables are separately Gaussian, but not jointly Gaussian. And you may want to see why, if variables are uncorrelated, in the Gaussian case, they are independent. So as you can see from the density function, it's quite straightforward. The off-diagonal entry will be 0 if they are uncorrelated. As a consequence, the joint probability density can be written as the product of the separate ones, right? Okay, this is the Gaussian distribution. So again, right here, you can see even from the samples you draw from the distribution, you can really see the difference between different distributions, right? In this case, for Laplace distribution, it's kind of sparse because very oftentimes with high probability, value is very small. And since you fix the standard deviation, also with a very high chance, the values are very large. Here we have different scales, right? And for uniform distribution, if you fix the standard deviation, then the range would be smaller. Okay. Why do we care about the Gaussian distribution, and why is the Gaussian distribution so popular? Right? Very oftentimes we use the Gaussian distribution. First of all, it's very simple, right? It's for the marginal distribution, or even for the multivariate Gaussian distribution, we just need two parameter vectors. And uncorrelatedness implies independence. That's perfect, because independence is the property of the whole distribution. Now, with only correlation, we can see whether they are independent if they are Gaussian. And we also know that approximately speaking, the distribution of the sum of independent variables will be Gaussian, will be approximately Gaussian if the number of independent variables is not very is relatively large. So this is central limit theorem. Of course, there are rather strong technical conditions for the central limit theorem. And very good. Now the next question. In this world, do you think most of the distributions you can observe or you deal with are Gaussian? Do you think they are Gaussian or non-Gaussian? There's none. Or do you think most, if you deal with the kind of variables in the world, right? Do you think most of the time the distribution are Gaussian or non-Gaussian?
I think non-Gaussian.
Non-Gaussian, why?
Life is complicated.
Actually, the Gaussian case is complicated, right? Because the total sum of an infinite number of independent variables, so complex. I'm kidding.
When they look at them, they are not Gaussian. I mean, maybe individually some of them may.
I agree with you. So I would say in most cases, if not all, distributions are not Gaussian. One reason is basically because of the Kramer decomposition theorem. Kramer decomposition theorem, I don't know why this theorem was kind of overlooked in the literature. It's very informative. It says the following thing. if the sum of a finite number of independent variables is Gaussian, then each of them is Gaussian. So if the total sum of a finite number of independent variables is Gaussian, then each of them is Gaussian. Okay, let me write down. So here, S equals finite number of independent variables, that yi are mutually independent. If S, the sum is Gaussian, then each of them is Gaussian. It's very strong, right? It basically means that, oh, suppose you consider finite number of independent variables, and if any component here is non-Gaussian, then the sum will be non-Gaussian, right? So that means that actually Gaussian variables just live in a kind of very small closed system as a closure property, because if you allow any non-Gaussian variable to enter this world and allow this non-Gaussian variable to interact with others, then finally all those variables will be non-Gaussian. Because as long as I have a non-Gaussian component, I'm non-Gaussian, right? Okay, so that's why in this world, most of the case, the distribution is non-Gaussian. And if you look at the central limit theorem, there's a condition on the coefficient, right? In the basic version, you assume all variables are ID, so they are independent and identically distributed. And even in the general version, there's a condition on the coefficient. So in most situations, according to Kramer decomposition theorem, variables shouldn't be Gaussian. That actually makes a lot of things so much easier. Why? Because we know that the Gaussian distribution is the limiting case. If you keep adding variables, right, and then finally we convert it to a Gaussian distribution, that means if you really observe the Gaussian distribution, it's already the equilibrium state, right? The process already converges. And if the process converges, then we don't have the process information because it's a point. Before that, the world is non-Gaussian. And later you can see that if variables are non-Gaussian, we can easily discover causality. Causality basically is the property of the process, right? So before you really reach the Gaussian distribution, you can discover causality in a very simple way. Okay. Good. And then here you can see illustration of central limit theorem. Good. All of you know it. I guess some of you read this book. I really like this book. It's chapter 7 of probability theory, the logic of science. Very good book. Chapter 7 of this book is devoted to the Gaussian distribution. And you can see why the Gaussian distribution is so weird. Why? Because this book gives 3 ways to derive the form of the Gaussian distribution. And each of them involves something very specific. For instance, in the first one, basically a long time ago, they try to measure the location of the star, right? And then you can have noise in X and you can have noise in Y, the 2 different axes. And if you assume that the 2 noise terms in X and Y are independent, and you assume that distribution is isotropic, meaning that after you apply rotation, the shape of the distribution is the same, right? Then you can derive that this is a Gaussian distribution. Only the Gaussian distribution could satisfy both conditions, both of them at the same time, right? One is the independence, the other is isotropic shape of the distribution. For instance, if you have this distribution, X, Y. So suppose this is a circle, and you have uniform distribution within the circle. Clearly it's isotropic, right? Clearly it's not Gaussian. Do you think it's do you think they are independent, X and Y? Uniform distribution within the circle. Do you think X and Y are independent? First of all, clearly they are not, because we know that if the distribution is isotropic, and if they're independent, then this guy must be Gaussian, right? So clearly they are not. And actually, you can see clearly that conditional distribution set of Y given X heavily depends on the value of X, meaning that X is very informative if you want to say something about Y distribution. they are not independent, right? Okay. And the second way to derive it is to basically enforce the condition that the maximum molecular estimation of the location is basically optimal one, is just arithmetic mean of the data. So if you assume that's the case, then you can derive that only when the distribution is Gaussian. This is true. And the last one to derive the Gaussian distribution is to assume to make use of some kind of stability. Suppose you have a distribution, you have a random variable with some distribution. Now you add some small noise or perturbation to the variable. Then you are going to have a new distribution, right? Because variance will be slightly larger. You are going to have a new distribution. And then if you assume that the form of the distribution is the same, then you can derive that that form must be the Gaussian distribution. So essentially, this is another way to make use of central limit theorem. Eventually, if the form does not change, then this form must follow the Gaussian function form. Okay. So from those derivations, you can see Gaussian distribution is so weird and so specific in this world and not Gaussian. Of course, in practice, it really depends on how many data points we have in order to discover and make use of the non-Gaussian part of the distribution, right? I think a lot of you look sleepy.
Can you go back to the previous slide? So the stability does not hold for the other distributions?
You mean which condition?
The stability.
Stability, last one.
Yeah.
No.
Okay.
You can see the derivation. Yes, it's a very beautiful derivation. You just have the differential equation and then you can solve it. Yes. Now we have probability measures, right? You can even have probability density function or probability mass function. Very simple, very intuitive thing is to see how two distributions are different, right? So how can you see? Suppose you have P, distribution P, and distribution Q, to probability mass functions or probability density functions. How can you evaluate the difference between the two distributions? One may say, oh, I can just use the squared distance, right? I can use the P minus Q squared, and then I can take the expectation, right? Or even without taking expectation, that's a valid distance measure, right? That's good. But if you use Kullback level divergence, a lot of things would be so much simpler, and it's directly related to a lot of other things, including maximum molecular estimation and mutual information and so on. So then that can make a lot of things so beautiful. This is the definition of Carroll divergence or Kullback level divergence. So it's nothing but the average of the log ratio, right? All the right here you have the log ratio, all the difference in the log density or log probability mass function. Then you take the sum or you consider expectation, right? So remember, we always use P, the first one, as a probability measure when you take the average. Okay, that's the Kullback level divergence. Now, for this measure, there's a very good thing. We know that this this divergence measure is non-negative, and that is zero if and only if the two distributions are identical. That's good. That means, oh, it's a very nice kind of measure of the difference. And the second one, we know that this guy is not symmetric. If you switch P and Q, the value can be different. However, you will preserve the sign. So if the Carroll divergence from P to Q is positive, then the Carroll divergence from Q to P is also positive, right? So it's still measured, although it's not symmetric. Okay, good. This is the Kullback level divergence. And then as a direct application of this measure of divergence, we can define mutual information. Again, now you can see we are trying to see whether variables are dependent or independent. So we know that for Kullback level divergence, we can just see whether two distributions are the same. If they are the same, then measure zero, otherwise positive. Then we can just measure the Kullback level divergence from the joint measure to the product of the separate marginal measures. If they're the same, they are independent. If they are not the same, they are not. So as you can see from here, mutual information between two variables or multiple variables is nothing but the Kullback level divergence from the joint probability measure to the product of marginal ones. Okay, so it's just directly followed from the definition. Look at those examples. In the first case, I have uniform distribution right here within this rectangle. Do you think they are independent? Do you think X and Y are independent? This is X, this is Y. Oh, sorry. Why? Yeah. So if they follow uniform distribution right here, do you think they are independent? Yes? Yeah. No? Okay, yes. In this case, still they follow uniform distribution right here within the square. Do you think they are independent? Okay, good, because the conditional distribution of say y, right, given x, clearly is sensitive to the value of x. Cool. Do you think they are uncorrelated? Do you think the correlation or covariance is 0? Yes? No? Do you think they are uncorrelated? I just try to make those kind of concepts intuitive. Later, we will make use of the difference between 0 correlation and independence. In this case, actually, they are not independent clearly, and at the same time, they are uncorrelated because covariance is nothing but the expected product after you center the variables. Here, you can see the product positive, right? And you can always find the same product with different sign. And then finally, the average the product will be 0, right? So here, the correlation will be 0. Later, you see this scatter plot once again. And with this, we can do causal discovery. You can see the asymmetry between two variables. Okay. I don't think I should give a summary once again. So essentially, the probability, the connection between probability theory and the statistical analysis, right? We make use of statistical analysis, then we can look into the kind of mysterious world and make prediction. I skip this part. Why can we do so? Basic connection is given by the law of large numbers. If you repeat the experiments a number of times under some conditions, the average in the statistical world will converge to the expectation in the probability world. That's why we can do something. We can analyze data, and then we can go further. Now we have to basically go down to the earth. We can only analyze data, right? How can we make use of data? So we can use the Bayes rule. We can do Bayesian inference. In Bayesian inference, it's cool because they are basically you don't optimize. You don't need to do optimization. Essentially, you don't have to do estimation. You just always follow the same principle to do inference. You have prior, you have conditional, right? And then you can find the marginal, you can find the conditional. For the parameters, you just care about the conditional distribution of the parameters given evidence, which is the posterior, right? It contains all the information you need, given the assumptions. So Bayesian inference is the standard, no matter how complex the problem is, and right, no matter how many layers you have for the model, you don't care. Just follow the procedure, you have the solution. Of course, in some cases, you may not have a closed form solution, but the underlying principle is there. Or from data, you can do parameter estimation with the maximum likelihood estimation, or some other kind of estimation method like Squamish investment method. Essentially, you want to find the best parameter value. Or you can do hypothesis test. In some cases, you just would like to see whether variables are independent. You want to give informative conclusion. And with hypothesis test is good because you don't care about the sample size, you don't care about anything. Finally, you can do calibration by making use of the p-value, right? This way, you still do of course, the final result will be sensitive to the sample size, but you have a way to calibrate the procedure. And then those three things are fundamental ways of making use of data or to derive conclusions from data. With those procedures, we can do a lot of things. We can do supervised learning, unsupervised learning, causal discovery, reinforced learning, and so on. By the way, causal discovery is a kind of specific type of unsupervised learning because you don't have label, right? You just try to find a way to look into the data to provide the structure. Okay, and linear regression is super simple. Let's just look at one thing regarding linear regression. Oh, I think one slide may. Okay, I may have deleted one slide. I'll try to bring it back later. So basically, for linear regression, suppose we have a regression line from X to Y, as you can see from here. Linear regression, you can use the ordinary least squares, or you can use maximum likelihood estimation. It's good. Now, suppose on the same coordinate system, you want to do regression in the reverse direction. You want to predict X from Y. You have a separate regression line, right? X hat equals beta times Y. This is a regression task in order to predict X from Y, right? So if you plot them together in the same coordinate system, where should the second line be? Should be here. The same should be here or here. So this is about the regression. The regression model in two different directions, right? And you see why. Which line do you think would be the regression line from Y to X? A, B, C. Okay, good, we can find. So we know for regression, if you consider product of the two coefficients, slope parameters, what's that? First of all, we can look at examples. Suppose X, Y are kind of weakly dependent or even independent. Then the original regression line will be here, right? It's a parallel to the x-axis. Where is the second line? Yeah, right here. Good. They are so different, right? And what if X and Y are kind of perfectly correlated without noise? Then they will be identical, right? So in the general case, should be somewhere in between. And furthermore, we know that here we have alpha and beta. Alpha is a prediction model from X to Y plus noise, and beta would be the prediction model to regress X and Y, C2. Then we know that the MLE of alpha and beta would be the sample cross covariance divided by the variance of the predictor, right? You can just derive, this is just an ordinary least squares estimate or maximum estimate of the coefficient. So what's alpha times beta? Covariance X, Y, sample covariance divided by variance of X, variance of Y, right? And what's this guy? This is just the squared value of the correlation, right? So this guy is smaller than or equal to 1 in absolute value, right? Smaller than or equal to 1. So only if this guy is 1 can alpha times beta be 1. If alpha times beta is 1, then the two lines will overlap, right? So generally speaking, alpha times beta is smaller than 1. What does it mean? The line would be B, right? If it's a line C, then the product of alpha beta will be larger than 1. Okay. So why do we have this kind of asymmetry? Because in regression, we assume there are noise in only Y, the target variable. There are no noise in X. That's why you can see regression clearly in different directions are not symmetric, because you assume noise is different and you have different ways to measure the noise, right? If you do regression from X to Y, you consider noise in this direction. Otherwise, consider in this direction, you have different lines. Okay. Oh, here. Okay. And then, should we take a break now or? Yeah, let's take a 15-minute break, and then after the break, you'll see how we can understand the graphical models and how to relate the graphical model to causality. Please come back in 15 minutes.